Welcome back. Today we are going to discuss about quantum error correction. Okay. So in this particular video, we will see how quantum error correction work. What are the types of quantum error correction? What are the real world applications we have in quantum error correction? Okay. So before going on to the quantum error correction, now I just want a quick recap. So how the errors will be there in classical computers. So a classical computer, you already know either it will be 0 or 1. For example, the bit has triple one, let us say. Okay, if it is flipping, or you can observe the error. So triple one to 101. That means it can be easily detected and which can be easily fixed in normal computers because bit can be copied. That you need to remember. If any error occurs, okay, the actual information will can be stored. Okay, so the classical error is simple, bits are either on or off. Okay, but whereas in quantum computers the data is stored in qubits that already I have discussed. A qubit can be 0 and 1 at the same time, which we call it as superposition. So you already know the equation, ket psi is equal to alpha ket 0 plus beta ket 1. For example, there is a 60% chance of being 0 and 40% of chance being 1 in this particular scenario. So why problems occur? So what is the reason the errors will be occurring in quantum? So qubits are very delicate. So can I can simply say qubits are very fragile. Okay, even tiny particles or tiny effects such as heat, magnetic fields, okay, cosmic rays, or we can say stray light, so these can destroy their state. Okay, these laws of quantum information we call it as decoherence. What is that? Quantum decoherence. So to build quantum computer that can do big calculations, we need a way to detect and correct these errors without actually measuring the qubit. Okay, what I am saying, without actually measuring the qubit. What happens if I measure? It will collapse the superposition state. So that is why we require quantum error correction. So that is the main reason. So quantum error correction does without measuring the qubit, it won't disturb the system, so the system will be in superposition. Okay, let's move on to one more slide. That is nothing but, so what is quantum error correction? Before going on to the types of quantum error correction, why I want you people to know what is quantum error correction. So quantum error correction protects quantum information stored in qubits. Okay, the information, you need to remember the information stored in qubits. Okay, this information will be handled without errors by using quantum error correction. Okay, it protects this information because if the information is lost, what is the thing we are making that all the calculation, there is no use, right? So it protects this information from noise. Okay, noise is like disturbance from the environment, that we call it as noise. Second one is nothing but decoherence. Decoherence is also nothing but loss of quantum properties. So and one more thing is nothing but it protects from operational errors. Let us say mistakes during quantum gate operations, etc., etc. These are nothing but operational errors. So it helps the qubit stay in quantum for longer, so it can complete the computations. Okay, so it can complete the computation, so it makes qubits to stay in quantum. So I have given one example here. Okay, so for example, think of vip. So vip is nothing but he will be having bodyguards, yes or no? So the bodyguards, here the vip is nothing but logical qubit. Okay, so the logical, in this particular scenario, the logical qubit is nothing but it stores information, that is nothing but wanted information or important information. Okay, it stores important information. Okay, logical qubit. Whereas the bodyguards here is nothing but we'll be using to protect the important information, that is nothing but helper qubits, we can say helper qubits to protect logic qubits. Okay, to protect logic qubits. Okay, So that is exactly what quantum error correction does. Okay, it protects one logical qubit using many helper qubits, same as VIP protected by the bodyguards. So now what is logical qubit? So as I already said, logical qubit is the one that holds the real information. What is that? That holds the real information. But a physical qubit is a hardware particle. It is nothing but hardware particles are nothing but like electron or superconducting circuit, okay, that carries the data and that protect the logical qubit. So there the main information will be there in logical qubit, but what does this physical qubits do is nothing but it protects them. It is like a bodyguard. So we do not store information in one physical qubit because it is too fragile. Instead we spread the logical qubit information across many physical qubits. What I said, we spread the logical qubit information across many physical qubit. Instead of taking one qubit for my operation, I take many qubits for my operation and I store this information in all those three qubits. If one error occurs, I can identify easily. So that is the main reason we will be using this physical qubits. Okay, for example, I am having 7 qubit system. Okay, 7 qubit system, okay, to represent only one logical bit or one logical qubit. Okay, if any error occurs in the 7 physical qubit system, this is nothing but 7 physical qubit system, so I can identify. So the 7 qubit systems are like this. So helper qubits may detect, for example, here if it is 0, helper qubit detects it as 0 and says that you need to apply some gate operations here to correct that error, but it won't be stopped or it won't be measured by the helper qubits. Will be knowing that there is some error occurring in the system, so we should need to fix it. So that is the main reason one logical qubit is equal to many physical qubits working together. So these many physical qubits working together is nothing but we call it as bodyguards for VIP. Okay, so now moving on to the types of quantum errors. So we'll be having bit flip error, phase flip error. In the next slide I will explain phase flip error. You already know bit flip error is nothing but ket 0 moving to ket 1 or ket 1 moving to ket 0. This is nothing but bit flip error. So if the bit was ket 0, okay, so due to noise, okay, it flipped to ket 1. So it can be easily identified and it can be easily solved also. So the bit flip error won't take much time or won't considered as the most impactful quantum error correction in this particular session. Okay, so but the main concern is about phase flip error. So phase flip error is nothing but this one is purely quantum. So it changes the phase of the qubit. So here if you observe, due to noise or due to some other vibration, that has been changed to minus. So you thinking of like just a minus we can be easily changed, but it cannot be easily identified, it cannot be easily changed. So what happens is nothing but this tiny minus changes the whole wave interference, and so called the final result can be completely gone wrong even though the values look similar. So here if you see the values, they look similar, but this minus symbol makes the calculations completely go in vain. Okay, that you need to remember. So this phase flip error is very tough to handle in quantum. Okay, now moving on to how quantum error correction fixes these errors. So as I already said, we cannot directly copy the qubits. So instead what we are doing is nothing but we are encoding one logical information into many physical qubits. Okay, so that makes us to correct some errors. So instead, if you see this example, so we'll be having only one logical qubit, but we are using two more helper qubits in both the cases. If one error occurs here, the helper qubit detect which one is wrong, so the system then flips it back to the correct state. Okay, that is what the thing we are doing with helper qubit. We call it as ancilla, and I will explain what is ancilla. And error is nothing but we call it as syndrome. In the next slide I have mentioned, okay, Ansel and syndrome. This you need to remember. These terms are very used, very widely used in quantum, okay, that you need to remember. So moving on to how this kind of quantum error correction fixes. One more slide I have explained. So these fixes the phase errors instead of bit flips. So we use Hadamard gate and CNOT gate for phase flip code, whereas for bit flip code we'll be using some poly X gate, poly Y gate, etc we'll be using. Okay, so one more example, this you need to remember, Shor's 9 qubit code. So this was invented by Peter Shor in 1995. Okay, so it combines both bit flip and phase flip error. Okay, it is not only like bit flip error, it is not only like phase flip error. So here one logical qubit they have done using 9 physical, okay, 9 physical qubits. Instead of obeying, or instead of giving only one logical qubit, they have added 8 more physical qubits to one logical qubit to have the calculations. Okay, even if one qubit gets disturbed, the overall quantum information cannot be lost, or it can be stored carefully. So that is the thing Peter Shor has been done in 1995. Okay, so now how these errors are detected? So if you look directly at the qubit to check off all these errors, it collapses. Okay, so using ancilla, what I mentioned, ancilla is nothing but helper qubits. These qubits won't directly interact or directly measure, but instead it is like friends. Okay, they are like friends. Okay, if one friend do wrong, then the other friend suggests that, or it say to teacher that our friend is doing wrong. So that is how ancilla will help our information qubit. Okay, so now ancilla qubits that interact with data qubits are nothing but information qubit that is having most information. They pick up the error information. So for example, error may be bit flip error or phase flip error. They will detect that error, and that error is called as syndrome. What is that? Syndrome. That you need to remember, syndrome. So without touching the main qubit superposition, the syndrome is detected without touching the main qubit superposition. So which is nothing but the wave function will not collapse, the wave will be in superposition, we don't have anything to lose. Okay, that is the reason we will be using quantum error correction. So think of one more example I can give you, like it is like a doctor. For example, if you are having a fever, so doctor won't check inside your body, they will check with just the thermometer. They learn what's wrong without opening you up. Okay, so ancilla, same here, ancilla qubit act as observers that tell us if something went wrong without destroying the quantum data. Okay, that is the use of ancilla. So now moving on to the steps. So how this quantum error correction occurs and what are the steps in that? So in the first step we will encode one logical bit. Okay, one logical bit into many physical bits, right? That is the first step. And if error occurs, when this error occurs due to noise or heat disturbance, okay, this error occurs. If error occurs, so what we do is nothing but there will be ancillas in the physical qubit, okay, in the logic qubit, in behind the logic qubit, that helps us to detect the error. That is nothing but syndrome. Will be, for example, syndrome is two types, as we know, bit and phase. So ancillas detect that particular error as bit or phase. Okay, then they will make correction. So the correction will be made using quantum gates, or if it is flip error, then we will be using X gate. If it is minus or phase error, then we will be using C0 or Hadamard gate to make it correct. Okay, then we are decoding the original logical qubit. That is nothing without measuring, we are doing inside that. Okay, throughout this process the quantum data remains protected and unmeasured. Okay, that you need to remember. Okay, remains safe and as well as unmeasured. So these are some quantum error correction codes. So 3 qubit bit flip code will be having only bit flip error, so simplest code for protection. But when you see here 3 qubit phase flip code, it is only having phase flip errors but correct phase errors. So this is somewhat tough compared to bit flip errors. Now moving on to Shor's Peters code, that is nothing but 9 qubits code, one logical qubit. It is done in 9 physical qubits, so it has both bit as well as phase. Okay, so this is the first complete Q, that is nothing but quantum error correction code combining bit and phase flip error correction. So one more it is nothing but Steno code that has 7 physical qubits. So it is having both, that is nothing but bit and phase, but it is more efficient for the version of source code. And moving on to one more type, surface code, they will be using many physical qubits, and the error will be of 2 types, that is nothing but bit and phase. And this is used by the real-time companies like IBM, Google, and even Microsoft also using surface code. Okay, this is more efficient compared to other various quantum error correction codes. Okay, now I will explain a quick example, okay, of surface code. So these qubits are arranged in 2D grid. Okay, in this such a way they are arranged in 2D grids. Okay, so each qubit interacts with its neighbor. So here one qubit will be there, here qubit will be there. They will be interacting each other. If here for example the information is 1, for example during the calculation here the error comes. Okay, this error we call it as syndrome. Okay, if the syndrome occurs, then helper qubit says the syndrome has been occurred, then we need to apply bit flip error. Okay, bit flip to regain the actual position. That is what the helper qubit do. Okay, this works on both bit flip and phase flip errors, so easier to implement on superconducting circuit hardware and works well on local connections. Okay, works well with local connection, that you need to remember. So here IBM 1000 qubit processor is used. So 1000 physical qubit are being used to protect only 10 to 20 logical qubits. Just think of how many number of qubits we require to build one logic qubits. Okay, so they are much reliable on physical qubits. Okay, that you need to remember. And moving on to some challenges and progress. So qubits lost information quickly due to coherence or fragile. Okay, so indirect measurement using ancilla adds noise. Okay, so these are some challenges. Each correction step adds tiny new errors. Okay, so systems need ultra cold minus 15 millikelvins. Okay, so these are some challenges. So progress of quantum error correction is nothing but in 2023 Google demonstrated a logical qubit that had fewer errors than physical ones. Okay, demonstrated a logical qubit that had few errors than physical qubits and reduced the error rate. So IBM in 2024 used surface code patterns in Condor chip. Okay, in Condor processor or Condor chip. Okay, we can say. So these are the key milestones towards fault tolerant quantum computing or quantum computers, systems that can run forever without crashing due to quantum noise. So these are the progress and these are some challenges. So this is about quantum error correction. If you are having any difficulty or if you are having any doubts, let me know in the comment section. Thank you.